Hey guys, so today we're going to be dealing with the chain rule. The chain rule is a rule that comes off pretty messy to explain in textbooks. Students get thrown off by it, and because there's a lot going on in the chain rule, and it's a rule that professors will have questions on tests that you'll have to use the chain rule, and they'll have a lot of questions like that because I don't know, the chain rule is just it takes more skill. It's one of those rules where you can embed the use of other techniques within it. So as we saw, like the product rule, where you have a product of functions and you want to take the derivative, but in order to take the derivative of each function on its own, you have to use some other technique, maybe the power rule or derivatives of trig functions. The chain rule is just like that as well. You're gonna have to be using other rules within the chain rule, and that's why the chain rule is very important, because it's a very encompassing rule. So it's very important that you understand it, because it's a professor's favorite on a test, and it's just very important because there's a lot of functions whose derivatives you just can't take without the chain rule. And we're gonna leave this video being experts. I'm gonna be doing a bunch of examples, so let's get into it. So what is the chain rule? Well, the chain rule helps us take the derivative of composite functions. So what do I mean by composite functions? Well, say I have f of x, and f of x is equal to f of u, and f of u is equal to u. So basically, I have a function, f of u is equal to u, and that's equal to f of x, big F of x. And say u itself is equal to g of x, and that is equal to the root of x cubed plus 2. So, well, substituting g of x in for u in little f of u, well, what do I get? Well, I end up getting this. I get f of g of x, and substituting in g of x in for u, I basically get x cubed plus 2. This is a composite function. G of x is a function on its own, and it is an input into f of u. It is an input. Therefore, I have a composite function. And you've seen this in pre-calculus, probably pre-calculus 12 or 11. Composite functions are usually taught there, and basically, it's just you have a function as an input. So, you have some other function, some more complicated function as an input into another function. So, well, the chain rule helps us take the derivative of functions like this. So let me just do some erasing. I'm going to show you what the chain rule says. And I'm just going to be using the same example, so I'm just going to get rid of the, a little bit of additional clutter. So, okay, so f of x is equal to f of u. And we're going to say u is equal to g of x. So I'm just going to make this arbitrary. I'm not going to give an actual function g of x or an actual function f of u. So we have f of x is equal to f of u. So big F of x is equal to f of u, and u is equal to g of x. So substituting in g of x for u, what do I get? Well, I get that composite function. And the chain rule says if I wanted to find the derivative, big F prime of x, what would that be? Well, that would be the derivative of little f at g of x times the derivative of g of x. So take a moment to digest that, because this is what the chain rule says. The chain rule is basically telling us, and listen carefully, because this is the meat of the video right here, is the chain rule is saying that when you have a composite function, what you do to take its derivative is to take the derivative of the outer function and multiply it by the derivative of the inner function. So you're going to be working outside, in. You're always going to be going from the outside and working inwards, thinning out the ranks of the functions, taking the derivatives until you have nothing left. And, well, we can have a composition of more than just two functions. And, that's going to help us, see this a little better. Usually with two functions, it may not, it may not tell the full story. So I'm going to add a third one. And just going to erase all this. Say we have, so I'm just going to erase this. And say big F of x is equal to f. And, forget the u. I'm just going to write the function straight. I'm not going to do the substitution. Say this is my function. Say f, the function f, relies on the function h as an input, and the function h relies on g of x as an input. Just going to make this, g of x as an input. You can also think of it like that, that one function is relying on the input of another function. So, the value of x affects the value of the function f at the end. So, getting back to this, so we have a composition of three functions. So, well, how do we take the derivatives? What does the chain rule say? Well, the chain rule says the derivative, like I said, we're going to be working outward, inward, taking the derivative of each function and multiplying it together. It's going to be f at h of g of x times. So we already took the derivative of f, and I said we're working outside in. So now we're not going to write f. We're going to take the derivative of h now. H at g of x. And then the derivative of g of x. As you can see, it's like, peeling something, maybe an orange. You're going from the outside inward. You're working through the layers. This function is just a layer of functions, and you're taking the derivative and just working through it. You're unraveling this function when you're taking the derivative of it. That's what you're doing. See how we did it? We thinned the ranks. We took the derivative of f. We thinned the ranks, and then we only had h and g left. We took the derivative of the function h. We thinned the ranks again, come to the function g, and we took its derivative as well. So that's basically what the chain rule says, and, I've written it, summarized it here. The golden rule is you're working outside, inward. And that's very, very, very important that you understand that, because that is basically, that's a very helpful idea to have. Have that visual image in your head that you're working outside inward, like you're peeling something or you're thinning the ranks. It's very important. So, another thing is that, it's very good to do some examples on the chain rule, because it's one of those rules that when you do examples, that'll really help you out. So let's do an example. So say we're given a function big F of x, and that is equal to root x squared plus 1. And this is one of the functions that, require the use of the chain rule. And, if you didn't have the 1 there, you could have just, used your exponent rules and used the power rule. But you have that 1 there, so you can't really simplify this any further. So, well, let's identify that outer function. And I think I'm going to use the substitution for this one just to illustrate more clearly what's going to happen. But we're going to get into the habit where, we don't have to, go through a tedious substitution just to, figure out the question. We can quickly identify the outer function and the inner function and know where to go from there. So let me illustrate. So let's say this big F of x is equal to f of u. So let's identify our outer function and our inner function. Well, what do we see here? The outer function is our square root. So you got the square root and you got something under it. That's your outer function. Your inner function is, well, what's under the square root. So it's a specific function under the square root. So let's say let me label this. This is our outer function. This is our inner function, right? So you got the square root acting on our inner function. That's our outer function. So let's see where to go from there. Let's say f of x is equal to f of u. And let's say our inner function, u, is x squared plus 1. So u is equal to x squared plus 1. And we'll say that's our g of x, right? As we did before, in a previous slide, we said u is equal to g of x, and that's x squared plus 1. I just didn't write it in that same order. So let's substitute everything in. So we got f of x, substitute in g of x. So you got f of g of x. And we're going to be working with, a little bit of notation rather than just, numbers right away. Just because I'm going slow in this first example. So substitute g of x in for u. And basically, g of x is x squared plus 1. Ignore this for a moment. Let's just work with the notation. So I want to find f prime of x. And, well, what did we say? We said outside in. So we take the derivative of the function f, and then multiply it by the derivative of g. Now, well, what was our function f? Well, f was f of u, right? This right here. Well, let's take the derivative of this. Just, we got the square root u. We got f of u is equal to square root u. And, u is equal to g of x, but let's take the derivative of this. Well, how do we do it? How do we find the derivative here? Well, you got root u. Remember root x? How do you take the derivative of that? Well, root x is just x to the half. So same thing here. This is just u to the half. So let's take the derivative. Well, that f prime of u is just half u to the negative half. So there we go. We got our first part right here, right? U is equal to g of x. So we got our first part, right? And I'm just going to do some erasing here. I'm going to erase this because we know that g of x is equal to that. So we got our first part right here. Do some erasing. And, it's good to write all this down. So there we go. We got our first part down. And what about our second part? Well, what did we say g of x was equal to? So now we found the derivative. We found our first part right here, f prime of g of x. Well, f prime of g of x was equal to f of u, and f of u is equal to the square root of u, and u is just a variable. So now you're just going to take the derivative as you would with x, and you come out to this. So, well, what is g of x equal to? Well, g of x, u was equal to g of x. And what was that equal to? Well, that is equal to x squared plus 1, right? So let's take the derivative of g of x. What's g prime of x? So we're doing with this part now. What's g prime of x? Really easy. It's just 2x, right? We learned how to take the derivative. It's just a polynomial. There we go. Done. 2x. So, well, let's put all of this together. Let's do it up here. Let's put all of this together. So I got f prime of x is equal to, let's just put in that u. So let's put our first part in. We found our derivative right here. Half u to the negative half times 2x, which was this part, right? So, well, we're not exactly done here because we want everything in terms of x. So what do we do? Well, we have this u, and what's u equal to? Well, u is equal to g of x, and what's g of x equal to? Well, it's equal to x squared plus 2. So what's f prime of x? Well, substituting in x squared plus 2 into this equation, well, you just get x squared plus 1 to the negative half times 2x. This is your derivative, big F of x. We're done. And, that took a little bit of time because we went slower, but, and, we did more substitution and I try to explain it. So, you're working outside in, and that's what we did. So let's do another example. So this time we're given a function f of x is equal to ln cosine x. Okay, so what's our first step? Well, first step is to identify the outer and inner function. So, the outer function is usually, it's acting on the inner function. So, who's acting on who right now? Well, the ln function is acting on cosine x. So, who's the outer function? Well, the ln function is the outer function. The logarithm of function is the outer function. This is our outer. And the cosine is our inner function. And, sometimes it's pretty obvious just by, a quick look at it, who's the outer and who's the inner function. Well, how do we take the derivative? Well, I think maybe I'll just do, like I did in the last question, just go a little slower and use the substitution. But, we'll get into I think I'll do a few questions or maybe a question or two without, doing the u substitution that we keep doing. Well, what's f of x? Let's say f of x is equal to f of u, and well, our outer function is the ln function, so this is going to be ln u. F is our outer function, f of u, and u is our inner function. And so if f is our outer function, f is going to be ln of u, and u is our inner function, so u is going to be g of x, and that's going to be equal to cosine x. Right? So, well, let's substitute g of x in for u. F of g of x, and this kind of seems a little cyclic that we created ln u and now we're just putting cosine back in, even though we were given it like that right at the start. So don't worry about this. What we do this is to get to see this notation a little clearer, and from here we're just going to work with the notation. So outside in, right? We're working from outside in. So what is f prime of x? And you got to get used to working with this notation if you really want to understand this. So, well, taking the derivative of the outer function first. So taking the derivative of f at g of x. Now taking the derivative of the inner function. So there we go. Big F prime of x is equal to little f prime of g of x times g of x. So now it's just a matter of, finding these derivatives. So our first one is this. Well, f of g of x is equal to f of u. And what is f of u? Remember, f of g of x is equal to f of u, and f of u is equal to ln u. So how do I take the derivative? How do I find f prime of u? Well, f prime of u, what's the derivative of ln of some, oh, that's x, don't worry. U. Well, what's the derivative of this? Well, it's just 1 over u. Right? So there we go. We found our first part. Done. And, we substitute g of x in for u, and g of x would just be cosine x, so that's just 1 over cosine x. And, well, what about our next part? G prime of x. So what's g prime of x equal to? Well, g prime of x is right here. It's equal to cosine x. G of x is equal to cosine x. What's g prime of x, though? What's the derivative of cosine x? It's just negative sine x. So what does this come out to? Well, this just comes out to 1 over u, but u is equal to g of x, so it's 1 over cosine x times g prime of x. Now the derivative of g of x, and that is just negative sine x. There we go. We basically just got negative tan x in the end. There's our derivative. And, illustrated it right there. So, you really got to understand, working with the notation and going outside inward. So this notation is really important, and that's why I'm doing the substitution, so you guys can see that. As you get more and more practice, you'll be, ditching the notation and just leaving it. So let's go on to another example, and this example is a little more interesting. And this example says, we got f of x, big F of x, and we're given a function ln x. This is our function. The ln of x. It's kind of hard to say, but this is a composition. When you look at this question, this is a composition of 3 functions. So, well, how do we break this down? So this is where I'm going to do a little bit of a transition from just, using substitution the whole time. So, well, let's say big F of x is equal to f of u, and that is equal to ln of u. And this is the outermost ln, right? This is our outermost function. Outermost. And then you got our next function, next outer function. Then we got our inner function. So, well, let's say f of u is ln of u. Just simplify this all, just shortened it. Well, u now is ln of ln x, right? So that's basically our inner function, you could think. Our next outer function and our inner function right there. And we're just gonna, so this is g of x. So, let's play with the notation a bit here. Let's not we have to simplify this, but let's not do it just yet. Let's say f of x, f of x is equal to f of g of x, right? And let's use our notation. What's f prime of x? Well, it's just f of g of x times g prime of x, right? So, well, let's fill in the blanks for this at least. So, what did we have? Well, we had f of u is equal to ln u, right? And how do we take the derivative of this? And u is equal to, g of x. So how do we take the derivative of this? Well, what is the derivative of ln u? Well, it's just 1 over u. So that's f prime of u right there. It's 1 over u. We got our first part. This is done. But now we got our second part, g of x. Okay, so what is g of x? How do we take the derivative of g of x? Well, g of x is right here. It's ln of ln x. And what do we see here? Well, we see another composition of functions. We have to do, another substitution, another composition of functions. But here's where, I'm not going to drag you guys through another composition. We have our outer function and we have our inner function. Well, what do? Well, we can treat this inner function, as we did before. We could just imagine it to be, a different variable, maybe w or whatever. And, we got our outer function and inner function. So we have g of x is equal to ln of ln x. So let's take the derivative of our outer function. Let's split this up. G of x equal to ln, so our outer. And I got ln x. That's our inner. And so what does the chain rule say? It says take the derivative of the outer function at the inner function. So what does that mean? Well, what's the derivative of the outer function? The derivative of ln. Ln of some input. What is the derivative of that? Well, it's just 1 over the input. You know, when we had just ln x on its own, what's the input? The input is x. What's the derivative? It's 1 over the input, and the input is x, so it comes out to be 1 over x. So what is the input here? Well, the input is ln x, the inner function. So what do I get? Well, g prime of x, what do I get? I get 1 over ln x. And, you know, what's the inner function? Well, the inner function is ln x as well. Sorry. The inner function is ln x as well. So what's the derivative of ln x now? The derivative of ln x is just 1 over x. So there we go. We took the derivative of our outer function and our inner function and multiplied it together. And that's g of x. So let's substitute this in here. Well, what do we get? So let me write it out. So what was our first part? Our first part was this, where we found f prime of u. And that is just 1 over u. And what is u? Well, u is just g of x. So what was that? That was ln of ln x. Now we wanted to take the derivative of g of x. And what did that come out to? Well, g of x was a composite function on its own. So we took the derivative of that, and we came out and we got ln x times 1 over x. There we go. We're done. This is the derivative. So you must realize that, you're going from outside in, and, that's exactly what we did here. We substituted, and, if I went on and did another substitution, it gets too messy and too cluttered. So you really got to make this connection really quickly that, you're going from outside in. So you got to sometimes, you got to start getting used to, skipping a few steps and just going ahead with it. You could do another substitution if you like, call this, a whole new function right up here, and then just, work through it on its own, and then just realize and substitute it back in. Or you could, we've already done a substitution, so you have something to, look at and visualize that you're moving from outside inward. So let's do another question, and this time I'm completely going to ditch the substitution. And we're just going to work with, just splitting it up and just thinking about it, So this is what I'm given. Y is equal to sine of x squared plus 2x. So what is our outer function? First thing to identify, our outer function. Well, it's sine. And in some textbooks, they'll actually split it up like this so you can see the derivative. So sine is our outer function. And what's our inner function? Well, this is our inner function. So this is our inner function. And well, what does the chain rule say? It says take the derivative of the outer function at the inner function. And when I say at the inner function, I mean leave that input alone. You're not going to take its derivative right away, right? You're going to multiply the whole thing. After you take the derivative of the outer function, you leave the same inner function input, and then you're going to take the derivative of the inner function, right? Because it's first the outer function's turn to have its derivative taken, right? There's a lot of that. I think I talked about that in the product rule too. Each function getting its own turn to have its derivative taken. Inner. So there we go. So we got our inner function, and let's take the derivative. So what's our derivative of our outer function? Well, the derivative of our outer function, what's the derivative of sine of something? Well, the derivative of our outer function sine is cosine. And we said we evaluate that at, the inner function. And the inner function is x squared plus 2x multiplied by, now it's time to have the inner function have its derivative taken. And what's our inner function? It's x squared plus 2x. So let's take the derivative of that. That's just 2x plus 2 plus 2, and we're done. Much quicker, much faster, just realizing what the outer function is and leaving it, evaluating at the inner function, taking the derivative, evaluating it at the inner function, times the derivative of the inner function. So remember, outside inward. Our outer function was sine of something, and that something was the inner function, which was x squared plus 2x. So let's do our last example. So our last example is, fairly easy, but, I'm illustrating that idea that we're ditching the substitution. So, I will do more questions in a tutorial video using the chain rule. So plus 20 to the power of 1,000. This question really helps illustrate why the chain rule is so important. When we get crazy functions, if you're not going to multiply this out, and even if you did had a computer multiply this out, taking the derivative by hand of this would take a very, very long time because you'd have very high powers. So let's take the derivative. This is why the chain rule is so useful. So what's our outer function? Well, our inner function, outer function is this. We got this exponent on something. Something to the power of 1,000. And what is the something? Well, the something is x squared plus 20. So you need to realize this, you have something, an outer function, acting on, maybe I shouldn't use something so much. So you have this outer function acting on some inner function. So who's acting on who here? Well, this power, this exponent, is acting on this binomial. Yeah, binomial. So let's take the derivative. Well, it's acting on this binomial, right? And just as when we use the power rule, if I were to, imagine a substitution of u here, I bring down the 1,000, right? Just as we did in the power rule. I took the derivative, the outside function, which was this power, this exponent, I brought it down, 1,000. Now I still got my inner function, right? So it's 20. And then, I used the power rule, and I got 999. Now let's take the derivative of our inner function, and what's that? That's just 2x. So, this one is maybe a little bit of an interesting example, Usually, when we did the power rule, like we just did right here, when we took the derivative of the second part, think of this whole thing as just some variable, like we did before, like u. So you got u to the power of 1,000. How do I take the derivative of that? Well, I use the power rule, and I just bring down 1,000 and get u to the 999, right? Think of it like that. And that's exactly what we thought of this binomial as here. And we just quickly did that, making these realizations, making these connections. And that's a lot of what calculus is about, is that, you got to make these connections, and you got to make them quickly. You can't just, sit there and, sometimes even go through super long processes just to figure stuff out. You got to be able to make these connections, and that's why practice is so important. You really got to practice in calculus, because it's one of those subjects. Math in general is just one of those subjects that just requires a lot of practice. It's not just, you can read something and then just go do a test or go apply it. You really need to do a lot of examples, even and odd examples in a textbook to really, really get a grasp of calculus in general. Like, you really got to work on that, and it requires a lot of dedication, and but it pays off in the end. So thanks for watching. I'll do a tutorial video on the chain rule. Like and subscribe. Tell your friends if they need help in calculus. They can always refer to this channel. I do my best to provide in-depth explanations, and my videos are long sometimes, but I just want to